My work is funded by partially by Newton, European project, and IRC, Research Council back in Ireland. So this presentation is broken down into 5 parts. First of all, the introduction, which will introduce the background of the technologies and the research goal. The architecture that's investigated, the algorithm that is proposed and how it functions, performance evaluation, the testing involved and results, and finally the conclusions and some future work remarks. So the research motivation focuses around these points. The video traffic is, as we know, is rapidly growing with increasing demand for quality. So with services such as Netflix, YouTube, Facebook, Instagram, all these providing so much content to the user. It's just growing and growing, and of course the user is expecting a higher quality of experience with the likes of 4K, 8K and future technologies, and mobile devices, of course, ever evolving. So current network infrastructure is not capable of supporting this explosion of data. We need to look at different approaches. We need to be able to cooperate, to choose different network technologies to support this and to be able to give a high QoE. Traditional IP-based networks, which we are used to, address-based solutions, are used typically look at the location of the content. So of course we request from a particular address. This can result in potentially requesting content across a long network. Of course there's solutions there to get around this. But as an example, back in Ireland, if you go 5 minutes outside of a city, you're lost, you won't get anything. So proposed future networks are moving away from this and towards a more content-based solution. So instead of requesting from a particular location, you're requesting for the content and you can get it from potentially anywhere. So this leads us to information-centric networking, which is a future network proposal which, as I mentioned, moves away from address-based networking to content or naming structures. So in theory, each naming or each piece of content will have a unique name. And this content will be able to be found, discovered by following a hierarchy such as in Linux or Windows, similar concept. So interests are sent out to request content, and as these interests propagate across the network, the data can then be returned by following the reverse path of said content, of the interest. Various projects have been proposed for ICN, or under ICN, including CCN, Content-Centric Networking, Named Data Networking, NDN, and one of the earliest, DONA. And this work we consider CCN as it's a stable and readily available version. The other technology that needs to be briefly introduced, which I'm sure most of you are familiar with, is adaptive multimedia streaming. Of course, it involves changing multimedia quality, which can be the frame rate or the resolution based on the network performance or the device performance, in order to improve the quality for the user, or if you're looking from the server. But in this case, we're looking at just the user. So from this, the MPEG group have proposed Dash a while ago, and it has rapidly become one of the most popular solutions for video delivery. It involves dividing content down into segments of equal temporal length from 2 to 10 seconds, typically, and encoding these segments at different quality levels. These levels are then described in an MPD, or these segments are then described in an MPD or media description, media presentation description. And this file is then sent to the client in order to request their content as they require. No adaptive mechanism is proposed in this standard, so the client can then choose the segments as they please, as they go through, going from quality level up and down to get the best performance. So Dash is well explored in traditional networks, but in ICN, new challenges are introduced, such as throughput is more tricky to calculate, and Dash just has not been looked at as much. So in this paper, we introduce a buffer-aware adaptive streaming solution over CCN. The aim is to improve quality of experience, QoE, by addressing some of the factors which have been shown to be the biggest influence on QoE, including stalling, which is pausing and playback, and quality switching, so regularly switching between levels, which just, if that's happening all the time, it's just going to be irritating and have a major impact on QoE. Yeah. So here you can see the architecture considered in this work, the basic architecture for CCN, which is made up of consumers and publishers, and of course access points and routers, where a consumer is a client like us, just looking to view content, get it in any way. They don't care particularly as long as it doesn't come in a bad quality or cost them a lot of money. And the publisher, who is typically the one that's publishing the content or creating it in the first place, depending on the service. So consumers in CCN will request content by sending out an interest, in this case to the access point, who is aware of the surrounding network. And this interest is then forwarded on to a location that the access point is aware the content is available. So in this case, it sends the interest to the router then knows that the interest or the content is available from the publisher, so it sends it on. The return then, sending the content from the publisher back to the consumer is just the opposite. It follows the opposite path of the interest, as can be seen here. But one of the useful things for CCN is, for example, if the consumer up top had previously viewed the content and had stored it locally, our requesting consumer, when they send out their interest, would get the content quicker because the access point will be available, or will be aware of this content being available closer. It will send the interest to the router and the consumer with the content, and the consumer will immediately send back the content if they're willing to. So the consumer level architecture can be seen here with some components typical in CCN, such as the content store. You can see the playback buffer in this case is important as we are considering the level of it. So as content comes into the content store, it is sent to the buffer to be played as we want it. The buffer is then responsible for sending on its status or its health to the adaptation module, which will then perform the necessary adaptation to decide what the future quality should be, and then send off an interest in order to request this quality. So, yeah, as you can see in the buffer, in this work, we have a full level above, for example, 70%, in which case we consider the buffer to be in a healthy position. And if it's below a certain level, say 20%, can be changed. It's in a very unhealthy situation and needs to be fixed rapidly. So this is where the solution comes in, the algorithm. It focuses on increasing and maintaining the health of this buffer, where the health is defined as the current level in relation to the maximum, so percentage. Based on the buffer health, different styles are taken, including aggressive, adaptive, or adjustment, and steady. And a state machine is introduced to handle the transition between these states. So, as you can see here, the 3 states, using the table on the side, you can see how the transitions occur. As the buffer is increasing with L, there's 3 thresholds that it is compared against: BU, BL, and BM. So lower, upper, lower, and middle buffer thresholds. So as the level goes above the upper threshold for the first time, it will transition into adjustment. Then as it stays above that, and as the number of segments consecutively received without a change in quality, it will go up to the highest state or steady state. Then as the level decreases for whatever reason, below middle and lower level, it will slowly go down between the 2 states, adjustment and aggressive. These states are described here, where aggressive is the first state that we begin in. It, as it says, it's an aggressive approach that starts off at the lowest quality level available, and just as quickly as possible tries to fill up the buffer so that we can avoid stalling and freezing at startup. As you can see in the algorithm, it requests a quicker rate as well, so it tries to reduce the amount of time it takes to fill the buffer. From here, once the buffer level gets up to a healthy level, we go into the adjustment level state, where the quality is adapted based on whatever algorithm you may want. In this case, it's just a progressive step up, step down method, and it still requests the content rapidly in order to try and keep the level at a healthy level. And yeah, the idea of adjustment is that it's seeking the quality that best suits the current conditions of the network. So it's going, in this state, we're going to have potentially rapid transitions going up and down, but after a certain number of successful segments, we consider the suitable quality level to be achieved, in which case we can go into the steady state and we continue to request at this level at a steady pace without having to worry about adaptation. In this case, if the buffer level does start to struggle, we will move it back down and adjust again as needs to be. But the idea of the steady state is to minimize the number of transitions once we are actually at a stable situation. So, in order to test this, number of scenarios are set up, 6 scenarios, for 2 separate studies. The first study considers the impact of background traffic on the performance. As you can see, S1 to 3 are for this situation. The number of background consumers are changed, but the number of routers are remain just at 1. So this means that the number of hops is a limiting factor, which was an interesting point for us. So these will run 5 times each and so on, using the NDN simulator built on top of NS3. NDN suggests that's for NDN, but it's also for CCN. Yeah. So study 2 considers the impact of the hop count on performance for S4 to S6. In this case, the number of background was remains at the highest level, just to be realistic. In this case, it's 20, which is realistically not too much, but it's what we went with for this one. And the number of routers are changed 5, 10, 20 to see how far the hops have to go. So this is looking at delay possibly introduced by having to go a long distance. So each of these scenarios is run for 3 different solutions, and non-adaptive over CCN. Previously introduced Dash over CCN, it's one of the first ones, and our updated study of BADASC. 4 metrics are measured: throughput, PSNR, PLR, and number of quality shifts, which, as mentioned, have been shown to impact the QoE. Okay. So here's the results for the first study. As you can see, the throughput for our solution is the best performing. This is due to a loss occurring in for the other 2 solutions, as well as as can be seen for DASC, the previous solution. Very high level of quality changing. So this, of course, is going to have a major impact on the user if they're having 80 quality shifts in the duration of 1 video. I don't have here the duration of the video, it slipped my mind. This is going to be a major impact. While on the other hand, our solution has a minimal number of switches, not quite 0, but it's not going to happen if you're starting at the lowest quality not to have 0. So yeah, and you can see also with packet loss and PSNR, our solution performs well with an average of around 40 dB for PSNR and a minimal to 0 packet loss. For DASC, there is a strange outstanding outlier for PSNR, which we were never quite able to pin down, which is probably just user error more than anything else, but it just didn't mention it before it's called out. Then for study 2, this is the number of hops. We can see there is little variation actually in the end, but you can see that as the number of routers increases, the solutions manage to maintain their performance, with the number of quality changes still reflecting badly for DASC. While you can actually see that the throughput for Dask is still suffering, and for BADASK it is remaining strong. And then for PSNR, we are maintaining a stable throughput, or stable performance across each. So, in conclusion, the buffer-aware dynamic adaptive streaming over CCN has been proposed, where buffer health is considered, and it has been shown to outperform the comparative work. Future directions of this would be to consider throughput prediction in ICN, which has been shown to have difficulties, to complement the buffer-aware solution, and also to consider mobility, the impact of mobility on the architecture. So, thank you, and any questions?